Now that we have a good understanding of how PVWatts works and what all the different fields mean, how to get help if we get stuck, all of these things, let's go ahead and step through an example. And for this example, I want to do a landfill that's near West Boylston, Massachusetts. This is a site that was recently listed on the Repowering website. It's been evaluated for renewable energy, and I think it'll be a good demonstration site to run an example on. So we'll go back to the home page on the PVWatts calculator, put in West Boylston, Massachusetts. And here's the map interface that we're all familiar with. And it looks like West Boylston is in a somewhat rural part of Massachusetts. So the closest weather file is in Worcester. So we will use Worcester, Massachusetts as the weather file for this analysis. And it's only about 9 miles from West Boylston, so that'll give us a really good analysis. In order to run an example on this location, we're going to have to use a couple of other resources in order to get inputs that we need for the PVWatts calculator. One thing that we need to know is we need to know what system size could we potentially put on this site. The best resource to use when mapping out a site and measuring the available area is the Repowering America's Lands Mapper 2.0. This is a useful tool. It's hosted on the EPA website. If you go to the Repowering America's Lands webpage, under the tools section down here, you can see the mapping and screening tools. It talks about some of the resources that are available. If you go down to the bottom, there's a portal which you can use to access the mapper. If you click on that, it'll launch this ArcGIS tool. There's a quick description of some of the data sets that are included in the tool, and then also a user guide. But this is a very powerful platform because there are a number of data layers for different renewable energy technologies. It has a listing of numerous sites around the country, but what we are interested in is looking at the site in West Boylston, Massachusetts. So if we put that into the search bar, it'll show us the town of West Boylston. Zoom out a little, you can see there are some contaminated properties around this area, but the one that we want to look at is the landfill property over here. And you'll notice as I'm sort of panning around here, different data summaries are listed down below in this matrix. So you can see sites in the general area, where they're located, what program they're in, and then there are links to additional pieces of information about the site. But for our purposes doing a site evaluation here, we want to know what the size of the property is, and there are tools over on the left hand side here right under the search bar that can be used to mark up the sites and also take measurements. So what we'd like to do is measure the parcel. This icon on the left is for measuring area. If you click on that and then just go around the perimeter. You can be as careful as you want with this and do a really detailed measurement. I'm going to go through here kind of quickly. And then if we just double click to close it. So it looks like this site, there is about 6.8 acres available, and typically on these ground mounted PV systems, it takes 5.5 acres to build a megawatt of capacity. So if we pull open a calculator, we'll take 6 0.8 divided by 5.5 acres per megawatt. And that'll give us a system size of about 1.24 megawatts. So based on this measurement and typical system layout, we should be able to fit a 1.24 megawatt or so size system. And just kind of generally looking at this map, it looks like this is about an ideal parcel. It's been cleared of any vegetation, so it's nice and flat. There are no trees. It's about an ideal location for PV. So after we have crunched the numbers on the system capacity, we can plug that back into the PVWatts calculator. 1240. So this is asking for the PV size in kW. So we need to convert from 1.24 megawatts to kilowatts. So to do that, you multiply 1.24 times 1,000. That'll give you 1,240 kW. So the next field that we want to fill out is module type. We'll leave that as standard because we're not sure what type of panel is going to be used just yet. For the array type, we could potentially look at one-axis tracking or two-axis tracking, but for the time being, let's leave that as a fixed open rack. The system losses, we'll leave that defaulted. For this example, let's put in a tilt equal to the latitude of the location. The reason we want to do that is because we want to see what the maximum production possible out of this system is. And in order to have the maximum production over the course of the year, you want the tilt of the system to match latitude. So for this location, we'll put in 42 degrees north. Azimuth, we'll assume that the system is going to be pointing due south. Take a look at the advanced parameters. This is a good default for DC to AC size ratio. The inverter, we'll leave that defaulted at 96%. And then the ground coverage ratio, we'll also leave that defaulted at 0.4. We're going to want to change the system type from residential to commercial because this is going to be a large commercial size system. And the average cost of electricity purchased from the utility, we'll leave that at 14 cents. So that was auto-populated based on the location that we selected. And that seems reasonable for this part of the country. If we wanted to put a more precise number in here, we could try to get a utility bill from the actual landfill site operations. We could look at the average utility cost for the serving utility in this area. There are a couple of different ways that we could try to dial this in, but for this kind of quick feasibility level example that we're looking at, let's leave this defaulted at 14 cents per kilowatt hour. So this system has the potential to generate a lot of energy, so 1,642,635. And that amount of energy would be worth about $227,000 per year. So we can use these numbers to start to get an idea of what kind of economics this system would have. So here again in the user comments, we could put West Boylston, Massachusetts landfill. We could download hourly results. Look at all of the calculations that went into the simulation. Could make plots with some of this if we wanted to. And then also review all of the assumptions and all of the inputs to the simulation to make sure we didn't input anything incorrectly. So everything here looks good. So the next step in determining system feasibility is to actually take these results and calculate things like simple payback period or net present value or levelized cost of energy. And for this example, we'll just calculate simple payback period because that gives you a really quick snapshot of whether this is a really good project, a really poor project, or somewhere right in the middle. Simple payback period is the total cost of a project divided by the total annual savings of the project. So that gives you the number of years that it will take for that investment to pay itself back in simple terms.